All right. Hello, everyone. Welcome to our nuclear physics unit. As you guys know, I'm going to be out for 2 weeks. This is going to be the intro to this unit, talk about what we're going to cover, as well as talk about the quantum model of the atom, which should be a review. Of course, you guys went over it last year, so it might be, be a little hazy. So we'll talk about what you need to know for this class. So to start, when we talk about the universe, there are four fundamental forces in the universe. The one that we've talked the most about is gravity. The two that we're going to talk about this unit are the strong and weak nuclear forces. And the one that we will not talk about in this class is the electromagnetic force. So there's a little bit of info here that actually talks a little bit about a subject that is not within the scope of our class. It talks about the standard model of particles. And the standard model of particles talks about the another particle that makes up subatomic particles called quarks, as well as another type of particle called a force carrier, which is for each fundamental force, there is a massless or sometimes a particle with mass that carries that force between the two objects interacting via that force. For the strong nuclear force, that is the gluon. For the weak nuclear force, that is the W and Z bosons. For the electromagnetic force, that is the photon, which is actually packets of light. So using the electromagnetic spectrum, light itself is what carries the electromagnetic force. And we will talk more about that when we talk about waves in our last unit of the semester. Then for gravity, the force carrier is unknown, but there are these particles that we're looking for are called WIMPs or machos, which would be good candidates that carry the force of gravity. But since gravity is the weakest force in the universe, we just do not know. And it is really hard to design an experiment to measure the weakest force in the universe with our current technology. So the relative strength, gravity, it extends forever. So the interaction of gravity extends forever. There's no hard place where gravity equals 0 if there's an object with mass, but its strength is extremely weak. The weak nuclear force is the second weakest of the fundamental forces, but it could only exist within a space that is times 10 to the negative 18th meters. So these are the spaces that, that small space exists within the nucleus of an atom, which we'll talk more about in this lecture. The electromagnetic force, which is like magnets, and also how ionic bonds and all of our chemistry works that you learned last year. It extends forever, and it is a pretty strong force. And then we get to the strong interaction or the strong nuclear force, which is the strongest force in the universe, but it could only exist within a space between the distance between two protons in a nucleus is when it activates, but it is stronger than any other force, so it is hardest to break. So before we talk about the nucleus, let's talk about our most modern model of the atom. The model that we briefly talked about in this class and that you guys went over last year is the Bohr model, where you know that electrons exist in orbits like planets around a sun, and the nucleus is in the middle with protons and neutrons. But this is not the case. The biggest thing to realize about electrons is that they will actually exist in clouds of probability around the nucleus, and depending on their characteristics or their measurements that you could take about the electron's orbit, that's going to give you the shape of the orbital. So to remind us of the subatomic particles, protons are positively charged in the nucleus. Neutrons are also there in the nucleus, and the combination of both of these will keep a nucleus stable. Electrons will exist outside of the nucleus, and as we went over with briefly with the accurate model of the solar system, and we did an example of the hydrogen atom and how far an electron is, these orbital clouds will be extremely far away from the nucleus. And the proton could be anywhere inside those clouds of probability, and we will not know where it is until we measure exactly where it is. So why do electrons exist in clouds of probability? Well, they're of such low mass that we could actually observe them to behave more like waves than particles. So there's this experiment that you could do where you could launch, let's say we're launching a bunch of electrons at a screen. So both of these are showed here. And there's two holes in that screen. If whatever you're launching behaves like particles, you expect them to just go through these two holes here and make two different piles. But if you're to send waves at the same screen, the waves would go through these holes and create their own, two sources of waves over here. And depending on how they interact, they will either destroy their hills or build on their hills, and you will get what is called an interference pattern on your screen. And when you do this experiment with electrons, when we expect them to behave like particles, they actually behave like waves and will form an interference pattern. So this wave-like property of electrons was something that led us to the quantum model of the atom, and that is the biggest difference, is treating electrons more like waves than like particles. So depending on the properties of the electron, like its orbital momentum, trying to remember what else. It's been a while since I took the class, but the main one being orbital momentum, you will get these different shapes for what the orbital will look like. So your classic s orbital, the p orbital, and then the higher orbital momentum orbitals being the d and the f orbitals. So what to know about electron orbitals in the case for a quiz and a knowledge check coming up. So know that they're negatively charged and they exist in clouds of probability. So a function that solves the probability of where the electron can be found in space around the nucleus. And if you look in this space, you will find the electron at a certain point. It'll start behaving more like a particle, which is another part of quantum mechanics that particles can behave like waves, and then when you measure them, they'll start behaving like particles. It's a very you know, not normal thing that we would expect, but it turns out that it is true. So different types of orbitals, depending on the electron state, how much energy it has, what spin it has, what momentum and orientation it has. And so this is what will give you the S, P, D, and F orbitals. And then there's also the G and higher energy orbitals that electrons can jump to when they're in an excited state, but we will not talk about those. So now talking about the nucleus, which is the main part of this unit. So they're composed of protons and neutrons, and they're bonded together via the strong interaction. Protons and neutrons are composed of quarks. So we'll talk about those quarks in a second. So the interactions that we will talk about in this unit do not discuss the mechanics of holding the system together, like how we discussed the mechanics of gravity holding, an object in orbit around another object. We will not be discussing the mathematics of this, of what holds these two together. Instead, our focus will be on the phenomena we see as a result of these interactions, which will be radioactive decay, fission, and fusion. So these are going to be the main topics that are covered in the introduction to this unit. So we'll start by you guys talking about the composition of an atom and periodic table, and you guys will also do a quantum model of the atom. After that, you'll do radioactive decay, go over the half-life equation, and then we'll do fission and fusion. And then we'll end this with a blog post project. So something that is cool, that is actually deals with the mechanics of nuclear physics, is talking about the standard model of elementary particles. All of our particles are made of up and down quarks, and a different combination of these quarks will give us protons and neutrons. But then we also have the electrons, and these quarks will be held together by gluons. So that's just to give you an idea of the mechanics of this. Again, we will not cover that, but it is there for you to look up and talk about. The mathematics that talk about this is something called quantum chromodynamics, which is a very cool name that actually uses color combinations to describe how these particles can go together. These quarks can go together with different charges of gluons. It is a pretty cool topic. So your task today will be to make a model of a quantum model of the atom, and then you could view the rubric on Canvas. And then there is also a reading the periodic table quiz that you will take. It's only 18 questions. Make sure you do that. take a screenshot of your final score and then post it on the necessary assignment for Canvas. So those are your two tasks. So, good luck. See you soon.